Math 1314, section IC1, spring 2022, Tyler Junior College. Homework 9.1 and 9.2. It's a single assignment. Inverse functions and exponential functions. Video 1, definition of inverse functions. We're going to merge two sections together into a single homework assignment. This was the plan all along, but it's also pretty helpful since we're getting close to the end of the semester, and we're a little short on time. Before we can define inverse functions, we must first define what it means for a function to be one-to-one. So we're going to define a new characteristic of a function. That characteristic is called one-to-one. And here comes the definition. A function f of x is one-to-one if, and really it should say if and only if, that's the definition. Can't get into the text box, so forget about it. A function f of x is one-to-one if and only if f of a equals b, and let's highlight this part. F of a equals b implies a equals b for any such values a and b in the domain of f of x. Well, that last part is just saying that these have to be numbers that we can put into the functions to begin with. But what the highlighted part in the red box is saying is, if we put in two numbers into a function and they come out equal, so f of a equals f of b, then being one-to-one means that your inputs were the same to begin with. A is equal to b. So another way to look at this in terms of inputs and outputs is, and I'm reading the third paragraph, if you will, third sentence underneath the red box. Another way to look at this is in terms of inputs and outputs of f of x. A function is one-to-one if the only way you can get equal outputs for a function is if you have equal inputs. Let's highlight that. The only way you can get equal outputs is if you have equal inputs. That's what the highlighted part in yellow up here is saying. If you have equal outputs, then you get equal inputs. Now, a lot of people don't think of it this way, but this is the same as saying different inputs yield different outputs. Excuse me. Because if your outputs were equal, then your inputs would be equal. So there's a few ways to think about being one-to-one, but the phrase one-to-one means 1x for every 1y and vice versa. Recall that some functions, you can put the same numbers in and, different numbers in and get the same numbers out. For example, if we have a function that says, I'm going to square you, I'm going to raise you to the second power, that if I take 5 and square it, I get 25. But if I take -5 and square it, I also get 25. So that wouldn't be one-to-one because I would have two different x's pairing up with one single y, one x to one y and vice versa. That's what makes a function one-to-one. And we got a couple of examples here. Let's just take a look at them one at a time. And to make it a little bit easier to follow, I meant to do this before we started recording, but here we are. We'll cover and reveal as we do this. For example, f of x equals the absolute value of x is not one-to-one. Why? And I want you to think about this. One-to-one means 1x for 1y and vice versa. Now, as a function, 1x will always produce 1y. 1x will always produce 1y. That's what makes a function a function. Every value in the range is paired up with exactly one value in the domain. So really, it's the other way around when you have to check for one-to-one. Is every 1y paired with just 1x? Well, another way of thinking about it is, can I think of two different inputs that would produce the same outputs? Is that possible? Well, let's think about this one. Remember, absolute value simply measures distance from 0 in terms of numbers. It leaves positive numbers alone and turns negative numbers positive. Observe that, for example, and I'm just using 3 and -3 as a specific example, f of 3 equals the absolute value of 3, which is 3, and f of -3 equals the absolute value of -3, which is also 3. Hence, we have f of 3 equals f of -3. The outputs came out to be the same, but 3 is not equal to -3. We have different inputs yielding the same output, and that is what violates being one-to-one. If you're one-to-one, different inputs are supposed to produce different outputs. That did not happen here. It's easy to show a function is not one-to-one. You just have to come up with what's called a counter example, come with two different numbers that when you stick them into the function, they spit out the same answer. So in this case, the two different numbers were 3 and -3, but they both came out to be the same answer. We had two x's pairing up with one y. 1 to 1 means one x pairs up with one y. We had 2 to 1, so not 1 to 1. It's a little bit trickier to show a function is 1 to 1. For example, f of x equals 2x plus 3 is 1 to 1. Why? Well, we're going to use the original definition in the red box that f of a equals f of b implies a equals b. In other words, we're going to start with f of a equals f of b and wind up with a equals b by doing some legit algebra moves. Okay, so let's suppose f of a equals f of b. Then using our function, this means 2a plus 3 is equal to 2b plus 3. Well, we could subtract 3 from both sides of this equation. The 3's would cancel on both sides and give us 2a equals 2b. And then we could divide both sides of this equation by 2. That would cancel all the 2's and give us a equals b. Thus, f of a equals b implies a equals b. In other words, we started here and we ended here. And so a equals b was a consequence of f of a equaling f of b. In other words, if we assumed that we had two equal outputs, that really meant that we had two equal inputs. And that's the definition being 1 to 1. Now, there's two ways to graphically verify a function f of x is 1 to 1, because sometimes if you have a graphic, you just look at it and go yes or no. Number one, the graph of y equals f of x is strictly increasing or strictly decreasing from left to right. What do I mean by that? Well, if you think of a graph as a roller coaster, then going left to right, the graph is only going up. So for example, if I graphed f of x equals 2x plus 3, and this is going to be a real rough sketch of it. It's in slope-intercept form, so its y-intercept is 3 and its slope is 2. So it looks a little something like that. From left to right, that graph is strictly increasing. And by contrast, when we had f of x equals the absolute value of x, that graph, you may recall, is a V shape. And so it's decreasing on the left side, meaning as we move from left to right, the graph is going down. The graph is going down, and then it's going up. Whereas in the other graph, it was strictly increasing from left to right. As we move from left to right, it's just going up nonstop. Another way to look at a graph and see if it is a one-to-one function is it passes something called the horizontal line test. The horizontal line test says if no horizontal line crosses the graph more than once, then the function is 1 to 1. For example, if I grab this horizontal line, we'll make it green. I grab this horizontal line here and I move it up or down, it's only going to cross the pink graph one time, no matter where I put it. So no horizontal line crosses this graph more than once. The function is 1 to 1. By contrast, if I take a horizontal line over here, except for hitting the corner, every other horizontal line that crosses the graph crosses it 2 times. That violates the horizontal line test. I invite you to think about why both of these things imply 1 to 1 in terms of inputs and outputs. I'm going to put that horizontal line back here just so it'll be saved in the PDF. All right, there's a lot to go over, so we'll go over it shortly. Here's why it's so important to talk about 1 to 1 first. A function f of x has an inverse if and only if f of x is a 1 to 1 function. So in other words, if you have one of these functions where equal outputs imply equal inputs, or vice versa, different inputs imply different outputs, then that function has an inverse. And when f of x has an inverse function, that function is called invertible. Excuse me. And there exists a second function, g of x, such the following are true. So in other words, if you're 1 to 1, then you have an inverse. You're called invertible, which means there is another function that does something in cooperation with you. These two functions together satisfy the following 4 criteria. Number 1, the domain of g of x equals the range of f of x. In terms of inputs and outputs, what this is saying is the numbers that can go into the second function g are precisely the same numbers that can come out of the first function f. and vice versa. The domain of f of x equals the range of g of x, meaning that the numbers that can go into the first function are precisely the same numbers that can come out of the second function. So together, what these are saying is any number that goes into one function can come out of the other, and vice versa. Number 3, and here comes some function composition. F of g of x equals x for all x in the domain of g of x. In other words, if we take and recall that f of g of x means, by definition, f of g of x is f of g of x. And so it makes sense that we have to say this is true for all x in the domain of g of x, because that number has to first go into g. In other words, it has to be in the domain of g of x. Now, why does it also have to be in the range? Because this guy is coming out of f. In other words, it's got to be in the range. So the reason the domains and ranges have to match is because this third thing says I'm going to put something into the g, meaning it's in the domain of g, and it will come out of the f, meaning it's in the range of f. So that's why we have the domain and range thing. And the fourth and final criteria is the reverse composition, meaning that g of f of x equals x for all x in the domain of f of x. And again, the reason it has to be in the domain of f of x for this criteria is because something like g of f of x means g of f of x. And so in this one, you have to go into the f function first. All right. Now, when such a function g of x exists, we say g of x is the inverse of f of x and vice versa, and write the inverse function as f inverse of x with a little -1 up there. For example, we're going to show that f of x equals 3x minus 7 and g of x equals x plus 7 over 3 are inverse functions. Now, normally I would bother with the domains and ranges, but I'll tell you right now that both of these are lines. This line has a slope of 3. This one's a little stealthier as a line, but this is the same as 1/3 x plus 7/3, and it has a slope of 1/3. And since both of these are lines with positive slopes, then their domains go left and right forever, and their ranges go bottom to top forever. So for both of these, both of their domains and ranges are all real numbers. And so we have the domain and ranges matching as necessary according to the definition. The domain of one equals the range of the other and vice versa. We're going to focus mainly on the composition aspect of it, starting with f of g of x. F of g of x by definition means f of g of x. And the way we did these before is you start on the inside and replace it with what it equals. Well, g of x in this problem is x plus 7 over 3. Now don't panic that that's a fraction, because now we have to do what f says to do. F says, give me something, I'll triple it, and then I'll add 7. Excuse me, I'll subtract 7. Well, what f is doing it to is x plus 7 over 3. And you'll notice we start getting some things that drop out. The 3's cancel, and that leaves us x plus 7 minus 7. And then the 7's cancel, leaving just an x. Well, we show that f of g of x is equal to x, so we're good. Similarly, and I'll spare you the details, I invite you to try it on your own. It's not that difficult. You'll see a lot of cancellation once you get it set up. G of f of x is equal to x. So I'm going to leave it to you to verify that the composition in the reverse order also gets the job done. All right, let's take a look at one more. Are f of x equals x plus 3 and g of x equals negative x plus 3 inverse functions? Well, we would have to first talk about domains and ranges, but again, both of these are lines and they're not horizontal or vertical, which means they go up and down forever and left to right forever. So both of these have the exact same domains and ranges, all real numbers. We just merely need to check the composition. Let's check f of g of x. Well, that's f of g of x. But we go to the inside and replace it. G of x is equal to negative x plus 3. And now we're going to do what f says. F says, give me something and I'll add 3 to it. All I did is take the f function, replace the x with an empty set of parentheses, and now I'm going to fill in that empty set of parentheses with whatever the content of this parentheses is. So negative x plus 3. And you'll notice the plus 3 and the plus 3 make a plus 6. The x still has a negative on it, and we end up getting negative x plus 6. But more importantly, this is not just plain old x. We did the composition, and it was not equal to x. So right away, we can say, therefore, these are not inverse functions, not inverses. One quick comment before I wrap up this video, and I'm sorry it seemed rushed. I started it when I thought I had time to make it, and I ran out of time, but we're getting it done. Back on this previous one, when we said that these are inverse functions, and I didn't actually say it here, so we'll say therefore inverses. I want to comment real quick on the notation. We could say that f inverse of x is equal to x plus 7 over 3. Now that's what g of x was, but by saying it that way, in other words, by saying f inverse of x equals x plus 7 over 3, we're connecting it directly to the original function f of x. So we're saying this is the inverse of a previously given function named f. All right.